Imagine drifting through the silence of space when suddenly your radio picks up something impossible, a deep, pulsing hum. No star, no galaxy, no known cosmic event could explain it. Yet there it is, echoing across the void, defying every law of physics we think we understand. This isn't science fiction. It's one of the universe's real, unsolved mysteries, a whisper from the cosmos that even the brightest minds can't decode. The truth is, for all our telescopes, probes, and equations, space still holds secrets that leave scientists speechless, unexplained flashes brighter than 1,000 suns. Planets that shouldn't exist orbiting dead stars, strange signals repeating with mathematical precision as if something or someone is trying to get our attention. These aren't just oddities, they're glaring gaps in our understanding of reality itself. That's why today we're diving into the top 25 astronomical phenomena science still can't explain. Each one is a cosmic riddle, a reminder that for all we've discovered, the universe loves to keep us guessing. Some of these mysteries might shake your view of reality. Others might make you question whether we're truly alone. But one thing's certain, by the end of this journey, you'll never look at the night sky the same way again. It was just an ordinary evening in August 1977 when astronomer Jerry Amon, scanning the skies with Ohio State University's Big Ear radio telescope, stumbled upon something extraordinary. A signal so powerful, so unusual, that it made him scribble one word in red ink on the printout. Wow! That single word would define a cosmic mystery that still haunts scientists today. The signal lasted exactly 72 seconds. A narrowband radio burst at the frequency of 1,420 MHz, matching the exact wavelength scientists predicted an extraterrestrial civilization might use. It came from the direction of the Sagittarius constellation with an intensity that dwarfed background noise by 30 times. And then, just as suddenly as it appeared, it vanished. Despite decades of searching, that exact signal has never been heard again. So what could it have been? Some argue it was a natural phenomenon, a comet's hydrogen cloud perhaps, or a rogue satellite reflection. But the Big Ear telescope's design made both explanations unlikely, as it filtered out earthly interference and would have detected other frequencies if a comet were the culprit. Others suggest a military transmission, yet no nation has claimed it, and its origin point moves with the stars, ruling out anything in Earth's orbit. Then there's the unsettling possibility. What if it was intentional? The signal's frequency sits eerily in the quiet zone of the radio spectrum, where cosmic noise is minimal, perfect for interstellar communication. Was it a fleeting hello from another civilization, a beacon we weren't meant to find? Without another whisper like it, we may never know. The WOW signal stands as a tantalizing enigma, a cosmic flare that burned bright and left us wondering, was it the universe playing tricks or something out there calling our name? One moment the cosmos is silent, the next, in a fraction of a blink, an explosion of energy erupts equivalent to 500 million suns bursting into radio waves, then vanishing without a trace. These are fast radio bursts, some of the universe's most baffling and violent enigmas. Lasting mere milliseconds, they pack more power than our sun emits in 80 years, firing from unknown corners of space with no warning, no pattern, and no explanation that satisfies every scientist. Take FRB 121102, the first repeating fast radio burst ever detected. Unlike one-off bursts, this one crackles to life again and again from a dwarf galaxy 3 billion light-years away. Its erratic cadence, sometimes silent for months, then flaring dozens of times in hours, has shattered theories about what could possibly power it. Magnetars, neutron stars with magnetic fields 1 trillion times stronger than Earth's, are prime suspects, but even their colossal energy struggles to account for the sheer force behind these bursts. Then there's the dispersion mystery. When FRB signals race through space, they interact with electrons, scattering their wavelengths in telltale ways. The more material they pass through, the more stretched out they become. Yet some bursts arrive with dispersion measures so extreme, they imply journeys through environments denser than any known galaxy. Are they traversing hidden clouds of ionized gas, or could their paths bend through warped spacetime near black holes? And yes, the wildcard theory lingers: artificial origins. The burst's precision and power have prompted a handful of researchers to ask, could these be signatures of alien propulsion systems or communication attempts? It's a fringe idea, but in the absence of definitive answers, even improbable possibilities get a hearing. Until we catch one in the act or trace a burst back to its birthplace, fast radio bursts will remain cosmic lightning strikes, brief, brilliant, and utterly bewildering. Picture holding a snow globe, except instead of water and glitter, it's filled with galaxies swirling in perfect balance. Now imagine trying to explain why those galaxies don't fly apart, even though the visible stars inside them don't provide nearly enough gravity to hold them together. That's the puzzle of dark matter, an invisible, mysterious substance that outnumbers the atoms we can see by a factor of 5, weaving through the cosmos like silent scaffolding. The first clues came from the way galaxies spin. In the 1930s, astronomer Fritz Zwicky noticed galaxies in the Coma cluster were moving so fast they should have torn themselves apart, unless something unseen was anchoring them with extra gravity. Decades later, Vera Rubin's observations of spiral galaxies confirmed it. Stars at the edges orbited just as fast as those near the center, defying Newton's laws unless invisible mass was propping up the whole system. But the smoking gun came in 2006 with the Bullet Cluster, a cosmic collision where two galaxy clusters slammed into each other. X-ray telescopes revealed ordinary matter, hot gas, piling up in the wreckage, while gravitational lensing showed most of the mass had sailed right through untouched. Proof that something invisible was bending space itself, completely separate from the atoms we know. So what is this ghostly stuff? The leading candidates sound like sci-fi, WIMP, or weakly interacting massive particles, theoretical heavy particles that barely touch normal matter except through gravity. Then there are actions, ultra-lightweight particles that could flow through the universe like a quantum breeze. But after decades of hunting burying detectors deep underground to shield them from cosmic noise, chilling them to near absolute zero, no experiment has definitively caught a dark matter particle in the act. The frustration grows when you consider how much of the universe depends on it. Dark matter's gravity sculpts the cosmic web, the vast filamentary structure where galaxies cluster like dew on a spider's silk. Without it, the night sky would be nearly empty, no Milky Way, no Andromeda, just scattered stars adrift in the void. Yet for all its influence, dark matter remains the universe's ultimate hide-and-seek champion, shaping everything we see while refusing to be seen. Some scientists are now daring to ask the unthinkable. Could we be wrong about gravity itself? Modified Newtonian dynamics, or MUND, suggests tweaking the laws of gravity to explain galactic motions without invisible matter. But even MUND struggles with evidence like the Bullet Cluster, so the hunt continues in tunnels under mountains, in particle colliders, even in ancient rocks that might hold fossils of collisions from dark matter's shadowy realm. Until we crack it, the cosmos keeps its biggest secret, a universe built on something we can't touch, can't see, but can't live without. If dark matter is the universe's hidden scaffolding, dark energy is its silent rebel, an enigmatic force pushing galaxies apart faster and faster, as if space itself has a mind of its own. Picture blowing up a balloon with dots on its surface. Now imagine the dots start moving away from each other faster as the balloon inflates, defying logic. That's precisely what astronomers saw in the late 1990s when studying distant supernova. These dying stars, known as standard candles for their predictable brightness, were fainter than expected, meaning they were farther away than the universe's age should allow. The shocking conclusion: the cosmos isn't just expanding, it's accelerating, propelled by something invisible that makes up 68% of everything. At first, scientists thought it might be a fluke. Maybe dust was dimming the supernova, but repeated observations from the Hubble Space Telescope to the Sloan Digital Sky Survey confirmed the impossible. A repulsive force dubbed dark energy is stretching spacetime itself. The real twist: Einstein predicted something like this a century ago. His cosmological constant, a mathematical fudge factor he later called his greatest blunder. Turns out he might have been right all along, yet dark energy's nature is a full-blown crisis for physics. Quantum theory suggests empty space should bubble with temporary particles, generating vacuum energy. But when you calculate how much energy that should contribute, the number is 10 to the power of 120 times larger than what we observe. That's like predicting a single raindrop, then getting hit with an ocean. Some theorists propose quintessence, a dynamic energy field that changes over time, while others explore modified gravity theories where Einstein's equations break down at cosmic scales. Then there's the Big Rip scenario. If dark energy strengthens over time, it could eventually tear atoms apart, unraveling reality itself. Or perhaps it's a sign of extra dimensions, or a holographic universe where our three-dimensional world is a projection of deeper physics. With experiments like the Dark Energy Survey and the upcoming Euclid telescope mapping billions of galaxies, we're hunting clues in the large-scale structure of the cosmos. But for now, dark energy remains the ultimate cosmic wildcard, an anti-gravity ghost rewriting the fate of everything. For decades, NASA Pioneer probes charted a course into deep space, becoming the first human-made objects to venture beyond the solar system, yet something was subtly, undeniably off about their journey. By the 1990s, scientists noticed Pioneer 10 and 11 were drifting off trajectory, slowing down just enough to defy predictions. Not by much, a fraction of a nanometer per second squared, but over years that tiny deceleration added up to thousands of miles of unaccounted drift. Dubbed the Pioneer Anomaly, this cosmic hiccup sparked a firestorm of debate. Were we seeing glitches in our understanding of gravity, or something far stranger? At first, the leading suspect was heat. The probe's radioactive power sources, called RTGs, emitted warmth, and even the faintest thermal radiation could, in theory, push back on the spacecraft like a whisper-thin break. Engineers crunched the numbers, modeling every bolt, wire, and surface, but the math never quite lined up. Some argued asymmetrical heat distribution might explain it. Others pointed to tiny gas leaks from thruster systems. Yet when they accounted for every known variable, up to 30% of the anomaly remained stubbornly unexplained. Then came the real curveball. Missions like New Horizons, which followed similar paths out of the solar system, didn't show the same drift. If thermal radiation were the culprit, why wouldn't it affect all spacecraft uniformly? This inconsistency fueled wilder theories. Maybe dark matter's gravitational pull was subtly tugging at the Pioneers. Or perhaps Einstein's theory of relativity needed tweaking at the edge of the solar system, where the sun's influence wanes. Some even proposed a modified inertia model, where the probes interacted with the universe's quantum vacuum in ways we couldn't yet measure. The mystery deepened when researchers realized the anomaly changed over time, decreasing as the probes aged. This pointed squarely at an onboard system, something degrading or shifting position. In 2012, a team meticulously reconstructed Pioneer 10's heat signature using decades-old blueprints and found the missing piece. Thermal radiation was the answer, but not in the way anyone expected. The heat wasn't pushing the probes evenly. It was radiating preferentially from their rear, creating just enough recoil to match the anomaly. Case closed. Almost a tiny discrepancy lingers, a ghost in the data that keeps the door cracked open for those who still wonder, could there have been more to the story? The Pioneer's legacy isn't just about solved puzzles, it's a reminder that even our most precise machines can become cosmic riddles. Sometimes the universe hides its secrets in the gaps between our best calculations, waiting for patient eyes to spot what everyone else overlooked. In the constellation Cygnus, a star named KIC 8462852 burns like a cosmic question mark, flickering in ways no other star should. Astronomers call it Tabby star, nicknamed after its discoverer Tabetha Boyajian, but it's better known as the star that made scientists openly consider, then reluctantly dismiss, the idea of alien megastructures. The mystery began in 2015 when Kepler Space Telescope data revealed its light was dipping erratically, sometimes by a staggering 22%. That's like watching the sun suddenly dim to the brightness of a crescent moon with no clear explanation. At first, natural causes seemed plausible. Young stars often host swarms of orbiting debris that block their light. But Tabby's star isn't young, it's middle-aged, with no trace of the warm dust that typically accompanies planet-forming chaos. Then came the curveball. Historical data showed the star had been dimming gradually by about 3% per century, as if something colossal was slowly eclipsing it over generations. Cue the alien megastructure frenzy. Astronomer Jason Wright floated the idea of a Dyson swarm, a hypothetical halo of solar panels built by an advanced civilization to harness the star's energy. The internet exploded with speculation, but scientists quickly pumped the brakes. Extraordinary claims need extraordinary evidence, and Tabby's star wasn't cooperating. Follow-up observations revealed its dimming was wavelength dependent, meaning shorter wavelengths of light were blocked more than longer ones. That pointed not to solid megastructures but to fine dust, likely the remnants of a pulverized moon or a shattered comet swarm. Yet even the dust theory has holes. In 2017, the star dimmed again, and this time the dip wasn't symmetrical. Instead of a clean U-shaped curve, the light dropped sharply and rebounded erratically, like someone flicking a cosmic dimmer switch. Dust alone couldn't explain that. Some researchers now suggest a giant, uneven dust ring, maybe from a catastrophic planetary collision, could account for the chaos. Others wonder if the star itself is unstable, with wild magnetic activity warping its light output. The latest twist, in 2021, a study proposed icy comet fragments spiraling into the star could explain both the gradual dimming and sudden dips. But critics point out that would require an implausible number of comets, millions, all on precise, destructive paths. With every new observation, Tabby's star dodges easy answers, leaving astronomers caught between mundane explanations that don't quite fit and the lingering thrill of something far stranger. It's a cosmic Rorschach test. Dust or Dyson spheres, comets or clever aliens for now. The star keeps its secrets flickering defiantly against the night. Stretching from Brazil to southern Africa, a vast region of space just a few hundred miles above Earth behaves like a cosmic glitch zone. A place where satellites sputter, computers reboot unexpectedly, and astronauts report sudden flashes of light behind their closed eyelids. Welcome to the South Atlantic Anomaly, often called the Bermuda Triangle of space, where our planet's protective magnetic shield wears dangerously thin. This isn't science fiction, it's a very real weak spot in Earth's invisible armor, and it's growing. At the heart of the mystery lies Earth's magnetic field, generated by the churning of molten iron in the outer core. Normally, this field deflects deadly cosmic radiation, funneling charged particles toward the poles to create the auroras. But in the South Atlantic, the field dips unusually close to the surface, creating a funnel where radiation from the Van Allen belts, twin donuts of energetic particles surrounding Earth, leaks through. Imagine wearing a raincoat with a single faulty seam. Even a small gap lets the storm in. The effects are dramatic. the Hubble Space Telescope avoids taking observations when passing through the anomaly to protect its delicate instruments. The International Space Station, though shielded, still experiences higher radiation doses here, forcing astronauts to retreat to more protected areas. And those eerie light flashes, they're caused by high-energy particles zipping through astronauts' eyeballs, triggering false signals the brain interprets as sudden bursts of light, a phenomenon documented since the Apollo missions. What makes this anomaly truly unsettling is its rapid evolution. Over the past century, the weak zone has expanded westward and weakened further, with some studies suggesting it might be splitting into two separate lobes. Some scientists tie this to larger shifts in Earth's magnetic field, including the gradual reversal of the poles, a process that's happened countless times in geologic history but never during human civilization. Others point to a dense region beneath Africa called the African Large Low Shear Velocity Province, where seismic waves slow dramatically, hinting at unusual heat or composition in the mantle that might disrupt the core's flow. Then there's the wildcard theory. Could the anomaly be a window into Earth's future? Simulations suggest our magnetic field might eventually resemble the chaotic, multipole structure of Uranus or Neptune, planets with off-kilter, patchy magnetic shields. Whatever the cause, one thing's clear: this cosmic pothole in space isn't just a navigational nuisance. It's a laboratory for understanding how planets protect themselves and what happens when that protection starts to fail. As satellites become more integral to modern life and human missions aim for Mars, decoding the South Atlantic anomaly isn't just academic. It's a survival skill for the space age. The Moon today is a silent, airless world with barely a whisper of a magnetic field, but drill into its ancient rocks and you'll uncover a startling secret. Billions of years ago, our closest celestial neighbor crackled with magnetic energy, a force field strong enough to rival Earth's. Apollo astronauts brought back samples in the 1970s that told this hidden story. Tiny mineral grains locked in place like compass needles, forever pointing to a time when the Moon was anything but magnetically dead. How could a world just 1% of Earth's mass generate such power? The leading theory points to a lunar dynamo, a swirling ocean of molten metal in the Moon's core, churning like Earth's but with a twist. Simulations suggest the Moon's early orbit may have been the key. Billions of years ago, it sat much closer to Earth, and our planet's gravitational pull could have stretched and squeezed its interior, stirring that metallic soup into a magnetic frenzy. Think of it like flexing a balloon filled with water. The motion creates turbulence, and in the Moon's case, that turbulence may have powered a magnetic engine for over 1 billion years. But here's where the mystery deepens. Around 1 billion years ago, the dynamo should have sputtered out as the Moon's core cooled and solidified, yet some lunar rocks show traces of magnetism from just 3.2 billion years ago, long after the dynamo's predicted expiration date. This timeline mismatch has scientists scrambling. Could impacts from massive asteroids have reignited the dynamo temporarily? Analyses of glass beads formed by ancient lunar eruptions hint at yes, their magnetic signatures suggest brief, violent bursts of activity, like a dying light bulb flickering before going dark. Then there's the shocker. Some newer models propose the Moon's outer core might still be partially molten, kept warm by radioactive elements like potassium and thorium. If true, it raises the tantalizing possibility of residual magnetic whispers even today, buried deep beneath the dust. But until we send more seismometers or even a drilling mission to probe the Moon's depths, its magnetic past remains a cosmic whodunit, a reminder that even familiar worlds can hide radical, unexpected histories. The Moon's lost magnetic field isn't just a lunar curiosity. It's a blueprint for understanding how small rocky worlds evolve and a cautionary tale for exoplanet hunters. If something as seemingly inert as our Moon once crackled with invisible energy, What other surprises might lie hidden on the countless moons orbiting distant stars? The answer is written in those ancient Apollo rocks, waiting for the next generation of scientists to decode their magnetic whispers. Galaxies aren't just drifting through space, they're racing towards something colossal, something with a gravitational pull so immense it bends the paths of hundreds of thousands of galaxies like a cosmic riptide. Meet the Great Attractor, a mysterious focal point roughly 250 million light-years away that's tugging our entire galactic neighborhood toward it at over 600 kilometers per second. But here's the catch: we can't see it, not directly, because this gravitational monster lurks behind the Milky Way's zone of avoidance, a thick curtain of stars, gas, and dust that blocks our view of the distant universe in that direction. Imagine trying to study a hurricane while standing in the eye of another storm. That's the challenge astronomers face. The zone of avoidance isn't just a minor obstacle. It swallows nearly 20% of the visible sky, obscuring the Great Attractor in a fog of cosmic static. Early attempts to probe this region with optical telescopes failed spectacularly, leaving scientists to rely on clever workarounds. Infrared and radio telescopes which pierced through dust revealed hints of structure, a dense knot of galaxies called the Norma cluster, tangled in filaments of dark matter. But the real shock came when researchers mapped the motion of galaxies beyond the Milky Way. Even accounting for the Norma cluster's mass, something far more massive had to be pulling us, something equivalent to tens of thousands of Milky Ways crammed into a space just 600 million light-years across. So what is this invisible titan? The leading theory points to the Laniakea supercluster, a vast web of galaxies spanning 500 million light-years, with the Great Attractor as its gravitational core. Think of it as the heart of a cosmic watershed where galactic rivers flow together. But skeptics argue the numbers don't quite add up. Laniakea's visible matter can't fully explain the acceleration. Some propose an even larger structure like the Shapley supercluster, lying farther beyond, whose gravity might amplify the pull. Others whisper about exotic possibilities, a concentration of dark matter so dense it warps spacetime, or even a primordial flaw in the universe's fabric left over from the Big Bang. The plot thickened in 2016 when astronomers discovered the Vela supercluster, a previously hidden mass of galaxies lurking even deeper in the zone of avoidance. Could this be the true source of the pull, or are we seeing the fingerprints of multiple attractors, their combined gravity weaving a web we're only beginning to trace? Every new observation peels back another layer, but the Great Attractor remains a paradox, a shadowy giant whose full nature might stay hidden until we develop telescopes capable of seeing through the Milky Way's cosmic blind spot. Until then, it serves as a humbling reminder. Even as we map the far reaches of the universe, some of its biggest secrets are hiding in plain sight, just out of view. On October 19, 2017, the Pan-STARRS telescope in Hawaii spotted something extraordinary, a faint dot of light hurtling through our solar system at nearly 200,000 miles per hour, on a trajectory so steep it couldn't have originated here. This was Oumuamua, the first confirmed visitor from interstellar space, and its bizarre behavior would ignite one of the biggest astronomy debates of the decade. At first glance, it seemed like a typical comet, except it wasn't. Most comets betray their presence with glowing tails of vaporized gas and dust, but Oumuamua stayed mysteriously dark, showing no signs of outgassing as it rounded the sun. Even stranger was its shape. Based on how its brightness flickered as it tumbled end over end, scientists calculated it was roughly 10 times longer than it was wide, an elongated cigar or pancake unlike any known asteroid or comet in our solar system. Natural objects just don't form that way. Then came the real stunner. After slingshotting past the sun, Oumuamua sped up slightly, as if pushed by an unseen force. The explanation should have been simple: outgassing. When comets warm up, they eject material, creating a natural rocket effect. but repeated observations by the Hubble Space Telescope and others found zero evidence of gas or dust, no coma, no tail, nothing. So what caused the acceleration? Some physicists suggested exotic possibilities like hydrogen ice sublimating invisibly, or even the object being a porous dust iceberg, light enough for sunlight alone to nudge it. But each theory had holes. Hydrogen ice would have vaporized too quickly in interstellar space, and sunlight's push couldn't fully account for the boost. Enter the controversy. Harvard astronomer Avi Loeb famously proposed Oumuamua might be artificial, a fragment of alien technology, perhaps a light sail propelled by starlight. The idea made headlines but divided scientists. Critics pointed out that unusual doesn't equal unnatural, and that we'd never seen an interstellar object before, so our expectations might be flawed. Others countered that dismissing the possibility outright wasn't scientific either. After all, if advanced civilizations exist, their debris should occasionally drift our way. The debate took another twist in 2020 when astronomers discovered a second interstellar visitor, 2I Borisov, a far more conventional comet with a clear tail. Its normality made Oumuamua seem even more anomalous. Was it a shattered shard of a Pluto-like world ejected from another star system, a rare type of nitrogen iceberg stripped from an exoplanet's surface? Or something else entirely? The frustrating truth is, we'll likely never know for sure. Oumuamua is now beyond the reach of our telescopes, a silent enigma racing toward the outer dark. It left behind more questions than answers, a cosmic passerby that forced us to confront how little we understand about what or who might be drifting between the stars. The next time an interstellar visitor arrives, astronomers will be ready. But until then, Oumuamua remains a tantalizing what if, a reminder that the universe is stranger than we dare imagine. The universe is unimaginably vast, with billions of galaxies each hosting billions of stars. So statistically, intelligent life should be everywhere, and yet when we listen, the cosmos remains eerily silent. This glaring contradiction is the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" To grasp the scale of the problem, consider the Drake equation, a framework for estimating the number of detectable civilizations in our galaxy. Plug in optimistic numbers, stars with planets, planets in habitable zones, the rise of life and intelligence, and the math suggests thousands, even millions, of civilizations could exist. But here's the catch: every variable is a gamble. We know planets are common, but how often does life emerge? If intelligence evolves, how long does it last before self-destructing or transcending? These uncertainties leave the equation balanced between hope and haunting ambiguity. Enter the great filter theory, the dark twist lurking behind the paradox. It proposes that somewhere between non-life and galaxy-spanning civilization, there's a near insurmountable barrier, a step so unlikely or perilous that it prevents most life from progressing. The terrifying question is whether we've already passed it. Perhaps the jump from single-cell to complex life is freakishly rare, or if it still lies ahead: nuclear war, AI catastrophes, or other existential traps. The silence of the cosmos could mean we're alone, pioneers in a sterile universe, or that advanced civilizations inevitably hit a wall. Other theories paint stranger pictures. Maybe advanced aliens aren't using radio waves, opting for neutrino signals or quantum communication we can't detect. Or perhaps they're deliberately avoiding us, treating Earth like a wildlife preserve, the zoo hypothesis. There's even the dystopian dark forest idea. Civilizations stay silent because broadcasting your location invites destruction from paranoid neighbors. Yet the simplest answer might be the most humbling. Space is big, time is vast, and our telescopes are young. Signals could be passing through unnoticed, or we might be like ants scanning a highway for signs of other colonies, missing the traffic roaring past. Until we find proof, the Fermi paradox remains a mirror, forcing us to confront how little we know about life's resilience or its fragility in the cosmic dark. The universe, statistically speaking, should be chaotic, random, directionless, yet when scientists mapped the afterglow of the Big Bang, they found something that defies that expectation. It's called the axis of evil, a spine-chilling name for a pattern in the cosmic microwave background that points eerily in one direction, almost as if the universe has a preferred axis. And if that sounds like it upends everything we know about cosmology, that's because it just might. The cosmic microwave background, or CMB, is the oldest light we can see, a snapshot of the infant universe just 380,000 years after the Big Bang. According to the cosmological principle, the foundation of modern physics, the universe should look roughly the same in all directions, with no special places or orientations. But in 2005, researchers analyzing data from NASA WMAP satellite noticed something unsettling. Large-scale fluctuations in the CMB weren't randomly scattered. They were aligned along a specific axis, like a cosmic fingerprint smudged by an unseen hand. Later observations by the Planck spacecraft confirmed it. The universe on its grandest scales appeared lopsided. Skeptics rushed to dismiss it as an instrumental glitch, a quirk of how we measure the CMB. Maybe satellite calibration was off, or foreground dust in our own galaxy was distorting the signal. But when independent teams accounted for every possible error, the alignment persisted. The odds of this happening by chance, less than 1 in 1,000. Suddenly, the cosmological principle, the bedrock assumption that the universe is homogeneous and isotropic, was on shaky ground. If the axis of evil is real, the implications are staggering. It could mean the universe isn't just expanding, it's rotating, a notion that would rewrite the laws of physics. Or perhaps we're seeing the gravitational imprint of a neighboring universe beyond our own, a bruise left by a collision in the multiverse. Some theorists even propose a cosmic defect, a relic crack in space-time from the Big Bang's first moments, frozen into the fabric of reality. But the most unsettling possibility, that we're wrong about the Big Bang itself. The standard model predicts a uniform, isotropic explosion, yet the axis of evil hints at structure before the universe began. It's as if someone whispered a secret into the cosmos's ear at the moment of creation, and we're only now learning to listen. Until future telescopes or bold new theories crack the code, this eerie alignment remains a silent challenge to our deepest assumptions, a cosmic riddle written in the first light of existence. Black holes aren't just cosmic vacuum cleaners, they're existential shredders, swallowing stars, planets, and light itself, seemingly erasing every trace of what falls in. But here's the problem: the universe hates losing information. According to quantum mechanics, every particle, every interaction leaves a fingerprint, a kind of cosmic receipt that should, in theory, be retrievable no matter what. Yet black holes, with their crushing gravity and event horizons, appear to break this fundamental rule. This contradiction is the black hole information paradox, and it's been keeping physicists awake for decades. The trouble started when Stephen Hawking made a startling prediction in the 1970s. Black holes aren't completely black, they leak. Thanks to quantum effects near the event horizon, pairs of virtual particles constantly pop into existence, one falling in, the other escaping. Over time, this Hawking radiation causes black holes to slowly evaporate, leaving behind nothing. No trace of the stars, gas, or unlucky spacecraft that fell in. Just empty space. That's the paradox. If information can't be destroyed, where does it go when a black hole vanishes? At first, physicists hoped the information might be encoded in the radiation itself, scrambled like a cosmic jigsaw puzzle. But calculations showed Hawking radiation is thermal random noise with no hidden structure, like ashes from a burned book. This led to two grim possibilities. Either quantum mechanics is wrong, unlikely, given its flawless track record, or black holes really are cosmic delete buttons, violating one of physics' most sacred principles. Enter the firewall hypothesis, a radical idea that suggests the event horizon isn't the smooth gateway Einstein predicted, but a searing wall of high-energy particles. Anything crossing it would be vaporized instantly, preserving information at the boundary while turning the black hole's interior into a no-man's land. The catch: firewalls defy general relativity, which insists falling into a large black hole should be uneventful. No walls, just the gentle tug of gravity. Then there's the holographic principle, a mind-bending solution that rewrites the rules of reality. It proposes that all the information swallowed by a black hole isn't lost inside, but is instead smeared across its two-dimensional surface like a hologram. Think of it like a movie projected onto a screen. The image looks three-dimensional, but every detail is encoded in flat pixels. Recent breakthroughs in string theory and quantum gravity suggest our universe might work the same way, with black holes acting as cosmic USB drives storing data in ways we're only beginning to decode. The latest twist: in 2020, physicists used quantum computers to simulate holographic black holes, finding tantalizing hints that information can escape, woven into the radiation's subtle patterns. It's not a tidy solution, more like a scrambled message in a bottle, but it keeps hope alive that the universe isn't playing by impossible rules. Until we crack quantum gravity or catch a black hole in the act of evaporating, the paradox stands as a stark reminder. Even the darkest corners of space might still hold secrets we're not meant to see. Saturn's North Pole is home to one of the most bizarre weather patterns in the solar system: a perfect, six-sided hurricane larger than Earth itself, spinning like a cosmic stop sign for over 4 decades. First spotted by Voyager in the 1980s and later studied in stunning detail by Cassini, this colossal hexagon stretches 25,000 miles across, with winds screaming at over 300 miles per hour along its razor-sharp edges. And here's what makes it utterly baffling: storms don't form geometric shapes, not naturally, not like this. On Earth, polar vortices are chaotic, swirling messes. Think of a pot of boiling water, with turbulent currents twisting in all directions. Yet Saturn's hexagon is freakishly precise, maintaining its six-sided symmetry for years without faltering. Scientists have tried replicating it in labs, spinning tanks of fluid at different speeds to simulate Saturn's atmosphere. Remarkably, they've created rough hexagons, but only under very specific conditions. The key seems to lie in the speed gradient between layers. Saturn's jet streams might act like nested cylinders rotating at different rates, shearing the storm into geometric shapes. Throw in the planet's lack of a solid surface, its low viscosity, and the Coriolis effect cranked up to 11, and you've got a recipe for atmospheric wizardry. But even these explanations don't fully crack the mystery. Why 6 sides? Why not 5 or 8? Fluid dynamics suggests that under certain conditions, turbulence can self-organize into polygons, but a hexagon this stable defies most models. Some theorists propose standing wave patterns, where high-altitude winds rebound off themselves like echoes in a canyon, locking the storm into shape. Others wonder if deep internal heat rising through Saturn's layers sculpts the vortex from below, like an invisible hand guiding the chaos. Then there's the strangest twist of all: the hexagon changes color with Saturn's seasons. As the planet tilted toward its summer solstice, Cassini watched the storm shift from a deep blue to a golden haze, likely due to sunlight triggering chemical reactions in its high-altitude haze. It's a reminder that this isn't just a static curiosity, it's a dynamic, living system, evolving in ways we're only beginning to grasp. The hexagon's persistence raises bigger questions about planetary atmospheres. If gas giants can harbor storms this precise and long-lived, what other freakish weather might lurk on exoplanets? We've spotted hot Jupiters with supersonic winds and molten iron rain. Could geometric storms be hiding in their swirling depths too? Until we send more probes or catch a glimpse of another hexagon out there, Saturn's North Pole remains a celestial art gallery displaying a masterpiece we still can't quite explain. In the quiet hours just after sunset or before dawn, when the sky is neither fully dark nor lit, an eerie glow sometimes rises from the horizon, a faint, tapered pyramid of light stretching upward along the path where the sun and planets travel. This is the zodiacal light, a cosmic phantom that has puzzled skywatchers for centuries. Unlike the auroras or Milky Way, this glow isn't made of stars or charged particles. It's sunlight reflecting off something far stranger, a vast, mysterious cloud of dust suspended in the inner solar system. At first glance, the explanation seems simple. Comets and asteroids constantly shed dust as they orbit, leaving behind trails that Earth plows through like a car driving through mist. Over time, this debris should settle into a flat disk along the ecliptic plane, the same band where planets move, but the zodiacal light doesn't behave the way it should. For one, it's far brighter than expected, suggesting there's more dust out there than our models account for. Even weirder, this dust isn't evenly distributed. Space probes have detected strange clumps and asymmetries, with some regions glowing noticeably brighter for reasons no one can yet explain. The plot thickens when you consider where all this dust might come from. Jupiter's gravity should have long since swept most of it away, yet the cloud persists. Some scientists point to Mars as an unexpected contributor. Its moon Phobos, slowly disintegrating under tidal forces, could be seeding fresh particles into the mix. Others speculate about a hidden population of asteroids trapped in resonant orbits, grinding against each other like cosmic sandpaper. Then there's the wild card, interstellar dust, grains drifting in from other star systems, might be weaving into the cloud, adding to its ghostly radiance. But the biggest enigma is the zodiacal light's flickering intensity. During the early 20th century, observers recorded it as vividly as the Milky Way. Today, it's often barely visible. Could solar activity be sweeping the dust away over time? Or are we seeing the aftermath of a colossal collision centuries ago, a shattered asteroid or comet that briefly flooded the solar system with debris? The answer might lie with NASA's upcoming Oumuamua mission, which will analyze interstellar dust grains in unprecedented detail. Until then, this ethereal glow remains a cosmic whisper, a reminder that even the space between planets holds secrets we're only beginning to uncover. Deep in the frigid outskirts of our solar system, beyond Neptune's orbit, lies a cosmic traffic jam, thousands of icy bodies swirling in the Kuiper belt, leftovers from the planetary construction zone 4.5 billion years ago. But something bizarre happens when you reach 50 astronomical units out, about 7.5 billion kilometers from the Sun. The belt doesn't gradually thin out like you'd expect. Instead, it hits a wall, a sheer cliff where the number of objects plummets by 90%, as if someone drew a line in the solar system and warned, no further. Astronomers call this boundary the Kuiper Cliff, and its existence defies every model of how planetary systems form. The leading theory blames an unseen giant, Planet 9, a hypothetical world up to 10 times Earth's mass lurking in the darkness. According to simulations, its gravitational pull could have shepherded Kuiper belt objects into clustered orbits while clearing out everything beyond a certain distance, carving the cliff like a celestial landscaper. Some calculations even suggest its orbit might be tilted, looping hundreds of O away before swinging back in, making it devilishly hard to spot. Yet after years of searching with telescopes like Subaru and Pan-STARRS, there's no direct evidence of this phantom planet, just circumstantial gravitational breadcrumbs. But Planet 9 isn't the only suspect. Others propose the cliff is a fossilized edge from the solar system's violent youth, when Neptune migrated outward, flinging objects into chaotic orbits or ejecting them entirely. Imagine a game of gravitational pinball. Some debris got slingshotted inward, some was tossed into the Oort cloud, and the rest were left stranded at 50O, marking the boundary where Neptune's influence waned. There's just one problem. Modern surveys keep finding a handful of objects beyond the cliff, drifting in no man's land. If Neptune's migration was the culprit, why are there any survivors out there at all? Then there's the wild card, interstellar interloper theory. What if, long ago, a rogue star passed uncomfortably close to our solar system, stripping away the outer Kuiper belt like a thief in the night? Computer models show such flybys were common in the crowded stellar nursery where the Sun was born. A close encounter could explain not just the cliff, but also the weird, detached orbits of objects like Sedna, which loop far beyond where they should. The mystery deepens every time we look harder. New telescopes like Vera Rubin Observatory might finally spot Planet 9 or force us to abandon the idea altogether. Until then, the Kuiper Cliff stands as a silent sentinel, guarding secrets from a time when the solar system was still finding its shape. Whether the answer is a hidden world, an ancient catastrophe, or something even stranger, one thing's clear: the edge of our cosmic backyard is nowhere near as quiet as it seems. For decades, astrophysicists have faced an embarrassing cosmic accounting error, one that makes misplacing your car keys seem trivial. When they tally up all the normal matter in the universe, the atoms making up stars, planets, and us, nearly half of it is missing. Not dark matter, not exotic particles, but regular protons and neutrons that should be lighting up telescopes like a neon sign. This is the missing baryon problem, and its solution might lie in the universe's hidden plumbing, a vast, diffuse network of superheated gas threaded through the cosmos like spider silk. The hunt began when researchers compared two ways to measure ordinary matter. The first method counts particles forged in the Big Bang by analyzing the cosmic microwave background, yielding a precise figure. Baryons should make up about 5% of the universe's mass-energy budget. The second method adds up everything we've actually observed: stars, galaxies, interstellar dust, and comes up startlingly short. Where's the rest? Enter the WIM, the warm, hot intergalactic medium, an elusive fog of million-degree gas lurking between galaxies. Theorized since the 1990s, this material is too hot to form stars but too tenuous to detect easily, like trying to spot individual water molecules in a steam room. The breakthrough came with distant quasars acting as cosmic flashlights. As their light travels through space, it gets subtly filtered by intervening material, imprinting faint absorption lines on their spectra. In 2017, astronomers studying the quasar 1ES1553+113 spotted the smoking gun telltale spikes from highly ionized oxygen, the fingerprint of WIM gas. Follow-up studies using the Hubble Space Telescope and XMM Newton found more traces, suggesting the WIM might store up to 40% of the missing baryons. But there's a catch: this gas isn't evenly spread. It clusters along the cosmic web, the filamentary scaffolding of dark matter that structures the universe, forming a labyrinth of invisible rivers too fine for current telescopes to map completely. That's where next-gen instruments like the upcoming Athena X-ray Observatory come in. Designed to detect ultra-faint X-ray emissions, it could finally reveal the WIM full distribution. Meanwhile, clever workarounds are emerging, like using fast radio bursts as probes. Since their signals disperse when passing through electrons, measuring this distortion could help weigh the WIM hidden reservoirs. Yet, even if the WIM accounts for all the missing matter, deeper questions remain. Why did baryons end up in this sparse, scorching state instead of coalescing into more stars? Simulations suggest galactic winds, outbursts from supernova and supermassive black holes, might have blown gas into intergalactic space early on, like a cosmic pressure washer. But until we can trace every atom, the universe's ledger remains unbalanced, a reminder that even the ordinary can hide in plain sight when you're not looking in the right places. The missing baryons aren't lost, just waiting, woven into the universe's invisible architecture. Most dying stars paint the cosmos with chaotic, swirling clouds, but one stellar farewell defies the rules with precision that borders on unnatural. The Red Rectangle Nebula, a cosmic masterpiece 2,300 light-years away in Monoceros, looks exactly like its name suggests, a glowing red box with an eerie X-shaped ladder of light at its core. This isn't some trick of perspective or camera artifact. High-resolution images from Hubble reveal a structure so geometrically perfect it seems almost manufactured, standing in stark contrast to the usual asymmetric blobs of gas we see in planetary nebulae. The secret might lie in its double act. Unlike most planetary nebulae which form when a single star sheds its outer layers, the red rectangle is shaped by a binary system, two stars locked in a gravitational dance. The primary star, a post-red giant, is ejecting material in dense, slow-moving outflows, while its smaller companion whips around it every 10 months. As the duo orbits, their gravitational tug channels the gas into two opposing cones, creating the nebula's striking X-shape when viewed edge-on. Think of it like two ice skaters spinning with a hose between them, spraying water in rhythmic arcs that freeze into perfect angles. But even that doesn't fully explain the rectangle's razor-sharp edges or its fiery red hue. The color comes from a rare form of carbon-rich molecules called polycyclic aromatic hydrocarbons, which fluoresce under ultraviolet light like cosmic neon signs. These molecules typically form in sooty clouds around dying stars, but here they've aligned with bizarre symmetry, as if the entire nebula is a stained glass window lit from within. Some researchers suspect the star's intense magnetic fields are herding the particles into orderly lanes, while others propose unseen planets or debris disks sculpting the outflow. Then there's the timing. Most planetary nebulae last just tens of thousands of years before dispersing a blink in cosmic terms. Yet the red rectangle structure suggests stability over millennia, a slow-motion eruption frozen in time. Could this be a preview of our sun's fate? In a few billion years, it too will shed its outer layers. Though without a binary partner, its death throes will likely be far messier. For now, the red rectangle remains a celestial oddity, a reminder that even in death, stars can defy expectations. Its perfect geometry whispers of hidden physics, of forces we're only beginning to map. And as telescopes grow sharper, who knows what other rule-breaking farewells we'll find, each one a puzzle waiting to unravel. On the rust-colored plains of Mars, a gas keeps appearing and vanishing like a ghost, one that might just hint at life. Methane, a molecule often tied to biological activity on Earth, has been flickering in and out of detection in the Martian atmosphere for decades. The curious part: it doesn't behave like methane should. Instead of dispersing evenly, it spikes unpredictably, sometimes tenfold in just hours, then disappears without a trace. This isn't just a scientific puzzle. It's a cosmic detective story where the prime suspects are either unseen microbes or geological processes we don't fully understand. The plot thickens when you compare the data. NASA Curiosity rover, sniffing the air inside Gale crater, has recorded repeated methane bursts, some lasting days, others mere hours. Yet Europe's Trace Gas Orbiter, scanning the entire planet from above, often detects nothing. At first, scientists assumed the discrepancy was a matter of timing. Maybe the orbiter missed the rover's fleeting spikes. But in 2019, the two missions performed a coordinated experiment, with Curiosity sampling the ground while the orbiter overhead analyzed the same airspace. The result: the rover found methane, the orbiter saw none. It's as if Mars is playing a prank, hiding the gas the moment we look away. So where's it coming from? On Earth, most methane is biological, belched by cows, leaked from wetlands, or exhaled by microbes in soil. If Mars methane is microbial, it could mean life persists underground, sheltered from radiation, perhaps in briny aquifers. But there are geologic options too. Serpentinization, a reaction between water and certain rocks, can produce methane, and Mars has plenty of both. Even meteorites constantly peppering the surface might deliver organic compounds that break down into methane under UV light. The trouble is, each theory has flaws. Biological methane would likely fluctuate seasonally as microbes respond to temperature shifts, but Mars spikes seem random. Geological processes should produce steadier emissions, not sudden surges. And if meteorites were the source, why don't other gases, like hydrogen, show similar patterns? Perhaps the most tantalizing clue lies underground. In 2021, researchers noted that methane spikes often follow Martian night, as if the planet exhales in its sleep. Could subsurface reservoirs be slowly leaking, with the gas only breaking through when temperatures drop and the soil's pores contract? Or more intriguingly, could a dormant ecosystem wake intermittently, releasing bursts of waste gas before retreating into dormancy? For now, the mystery endures. Future missions like the Mars Life Explorer aim to drill deeper and analyze isotopes, carbon signatures that might distinguish biological from geological origins. Until then, Mars methane remains a whispered rumor, a wisp of possibility drifting through the thin air of a world that refuses to give up its secrets easily. Whether it's the faint breath of life or the groan of ancient rocks, one thing's clear: the red planet still has stories to tell. Among the billions of galaxies swirling through the cosmos, Hoag's object stands apart, a celestial bullseye so flawless it looks almost artificial. Discovered in 1950 by astronomer Arthur Hoag, this rare ring galaxy floats 600 million light-years away, its golden core encircled by a perfect loop of young blue stars, separated by a hauntingly empty gap. Unlike most spiral galaxies with their tangled arms or barred centers, Hoag's object has no connecting structures, no visible threads linking its core to the outer ring. It's as if someone dropped a pebble into a cosmic pond, freezing the ripples into starlight. Theories about its origins split into two camps: catastrophe and calm. The leading idea involves a violent collision billions of years ago, where a smaller galaxy plowed through a larger one's center, sending shockwaves that triggered star formation in a ring. Picture a stone dropped into milk. The splash creates a circular wave, just as the impact might have sculpted Hoag's outer ring. But there's a problem: the core shows no signs of disruption. No warped dust lanes, no lingering asymmetry, just serene, undisturbed aging stars. If a collision happened, it was eerily precise, like a bullet passing through an apple without leaving an exit wound. Then there's the resonance theory, a gentler explanation where internal forces, not external trauma, shaped the galaxy. Stars and gas orbiting the core might have been nudged into a density wave, a gravitational ripple that compresses material into specific zones, like traffic bunching up on a highway. Over time, this wave could have funneled gas outward, sparking star formation in a ring while leaving the center pristine. Proponents point to computer simulations where isolated galaxies, under just the right conditions, spontaneously form rings without any collisions. But why, then, are ring galaxies like Hoag's so vanishingly rare? The answer might lie in timing. Ring structures could be fleeting phases, cosmic illusions that vanish within a few 100 million years as the outer stars disperse or the core exhausts its fuel. Hoag's object might simply be a lucky snapshot of a transient stage, one we've caught in a universe where most rings have already faded or haven't yet formed. Supporting this, Hubble images reveal a second, fainter ring nestled inside the main one, hinting at multiple epochs of star formation, like tree rings marking growth cycles. But the real enigma glows just beyond the main ring. Another galaxy, eerily similar to Hoag's object, floats in the background. Is it a clue, a long-lost sibling from an ancient interaction? Or just a trick of perspective? With only a handful of similar galaxies confirmed, Hoag's remains a cosmic loner, challenging our assumptions about how galaxies evolve. Future telescopes like the James Webb might peek into its dust-shrouded gaps, hunting for hidden structures or chemical fingerprints of past violence. Until then, this perfect ring floats in silence, a galactic riddle wrapped in starlight. In a universe teeming with galaxies, superclusters, and filaments of matter, there exists a cosmic desert so vast and empty it defies comprehension. The Boötes void stretches 330 million light-years across a staggering bubble of near-nothingness where only a handful of galaxies drift like isolated ships in an ocean of darkness. If you placed the Milky Way at its center, our nearest galactic neighbors would be almost impossibly distant, their light taking hundreds of millions of years to reach us. This isn't just a quiet corner of space, it's a yawning chasm that challenges our understanding of how the cosmos organizes itself. The first hints of this void emerged in the 1980s when astronomers mapping galaxy distributions noticed a bizarre blank spot in the constellation Boötes. Where they expected thousands of galaxies, they found fewer than 60 scattered across an area that should have held thousands. At first, skepticism ran high. Maybe it was an observational artifact, a zone obscured by dust or instrumental error. But deeper surveys confirmed the impossible. The Boötes void was real, and it flouted every rule about how matter should be distributed. To grasp how unnatural this emptiness is, picture the universe's large-scale structure as a spider's web, with galaxies clinging to dense filaments interspersed with smaller gaps. Most voids are expected bubbles a few tens of millions of light-years wide, formed as gravity pulls matter into interconnected walls, but the Boötes void is different. It's not just a gap in the web, it's a tear, a region so devoid of mass that some theorists argue it shouldn't exist at all. If the cosmic web is a sponge, this void is a hole big enough to swallow entire clusters without a trace. Explanations range from the statistical to the surreal. One camp argues it's a fluke, a low probability but inevitable outcome of random density fluctuations in the early universe. Run enough simulations of cosmic evolution, and eventually one spits out a void this extreme. Others propose more exotic origins, like the collision of multiple smaller voids merging over eons, or even remnants of an ancient phase transition, a crack in space-time left over from the universe's infancy. Then there are the whispers of something stranger. Could the void be evidence of a multiverse, where a neighboring universe's gravitational pull siphoned matter out of ours, or perhaps the imprint of a supercivilization that harnessed the energy of galaxies on an unfathomable scale? While these ideas linger on the fringe, they underscore how deeply the Boötes void unsettles our cosmic assumptions. Despite its emptiness, the void isn't entirely lifeless. The few galaxies within it, like the lonely spiral MCG plus 05366018, burn unusually blue, their stars younger and more active than expected. Some researchers speculate these outposts survived by cannibalizing their neighbors, merging in isolation to form rare, star-rich oases. Others wonder if the void's extreme environment altered galactic evolution entirely, forcing stars to form under conditions we've never seen elsewhere. For now, the Boötes void remains a paradox, a blank spot on the map that refuses to fit any tidy explanation. As telescopes like the Vera Rubin Observatory scan deeper and wider, they might uncover more of these cosmic anomalies, forcing us to rewrite the rules of structure formation. Until then, this giant pocket of nothing stands as a humbling reminder. Even in a crowded universe, emptiness can be the most mysterious thing of all. Galaxies shouldn't exist without dark matter. At least that's what every model of cosmic structure tells us. The invisible scaffolding accounts for 85% of the universe's mass, dictating how galaxies form, spin, and cluster. Yet in 2018, astronomers stumbled upon a cosmic heretic, NGC 1052DF2, a ghostly galaxy in the constellation Cetus that appears to defy this universal rule. Unlike every other known galaxy of its size, DF2 stars move sluggishly, their velocities too slow to be held together by visible matter alone. Subtract dark matter's gravitational glue, and this sprawling collection of stars should fly apart like a shattered snow globe. But somehow, against all odds, it doesn't. The discovery sent shockwaves through astrophysics. DF2 is an ultra-diffuse galaxy, a faint, wispy structure with barely 1/200th the stars of the Milky Way, yet stretching just as wide. Normally, such spindly galaxies should be drowning in dark matter to compensate for their lack of stellar gravity. Instead, measurements of DF2's globular cluster's tight knots of ancient stars orbiting its core revealed motions consistent with no dark matter at all. It's like finding a skyscraper standing tall without steel beams, held up by nothing but window panes. Skeptics pounced on a critical flaw: distance. If DF2 were closer than thought, its true size and mass estimates would shrink, potentially resolving the anomaly. Initial measurements placed it 65 million light-years away, but follow-up studies using Hubble's keen eye suggested it might be 20 million light-years nearer. That adjustment could shift calculations enough to sneak dark matter back into the picture. Yet even with revised distances, DF2 stubbornly refuses to fit expectations. Its stars still move too slowly, its structure too fragile for conventional models. Then came the plot twist. In 2021, researchers found another dark matter-deficient galaxy, DF4, floating near DF2. Both dwell near the massive elliptical galaxy NGC 1052, leading to a radical theory. Perhaps these oddballs were once normal galaxies until a violent encounter stripped away their dark matter. Picture a cosmic mugging. NGC 1052's gravity could have ripped the invisible halos from these galaxies during a close pass, leaving only naked stars behind. Computer simulations show such tidal stripping is possible, though critics argue the process would likely shred the galaxies entirely, not leave them intact. The implications are staggering. If galaxies can form without dark matter, it challenges our fundamental understanding of how structure emerges in the universe. Worse, it might hint at gaps in our gravity theories. Perhaps dark matter isn't the only answer, or our models of it need revising. Some theorists propose alternative explanations. Maybe DF2's dark matter is heated up, scattered into an undetectable haze by ancient supernova. Others wonder if we're seeing the aftermath of a bizarre collision that ejected dark matter like confetti. For now, DF2 remains an enigma, a cosmic rebel that refuses to play by the rules. Its existence forces us to confront uncomfortable questions. Is dark matter more nuanced than we thought? Are there multiple paths to galaxy formation? With every new observation, this ghostly outlier tightens its grip on one of cosmology's most cherished assumptions, proving that even the universe's deepest truths might have exceptions waiting in the dark. At the edge of the observable universe, where the first starlight flickered into existence, sits a cosmic impossibility, Oumuamua J1342+0928, a supermassive black hole so ancient it shouldn't exist. Clocking in at 800 million times the mass of our Sun, this ravenous giant was already fully grown when the universe was a mere 690 million years old, a cosmic toddler by galactic standards. To put that in perspective, imagine finding a skyscraper in the ruins of a civilization that had only just discovered fire. The existence of such a monster so soon after the Big Bang throws our entire understanding of black hole formation into chaos. Traditional models say supermassive black holes start small stellar remnants left by the death of massive stars, which then grow over billions of years by swallowing gas, dust, and other black holes. But Oumuamua J1342+0928 didn't have time for that leisurely feast. Even if it formed from the very first stars and ate non-stop at the maximum possible rate, it couldn't have bulked up that quickly under known physics. The math simply doesn't add up. This quasar's existence suggests either black holes grew far more efficiently in the early universe, or they skipped the starting small phase entirely. That's where the radical direct collapse theory comes in. Instead of forming from dying stars, these black holes might have been born heavyweight, collapsing directly from giant clouds of primordial gas under extreme conditions. Picture a cosmic shortcut, dense pockets of hydrogen and helium in the infant universe, unpolluted by heavier elements, collapsing so violently they bypass star formation entirely, birthing black holes tens of thousands of times the Sun's mass in one catastrophic step. These seeds could then balloon into supermassive monsters by gobbling up the surrounding gas-rich environment, but even this daring idea has problems. Direct collapse requires near-perfect conditions, no nearby supernova stirring up turbulence, no contaminating metals to fragment the gas into stars first. Simulations show these pristine, atomic cooling halos were rare, yet Euler's J1342+0928 isn't alone. Other quasars nearly as old and massive lurk in the early cosmos, hinting at a population of rule breakers defying the standard timeline. The implications rewrite cosmic history. If direct collapse black holes were common, they would have reshaped their surroundings dramatically, heating intergalactic gas with their radiation and altering the pace of star formation across the universe. Some researchers even speculate these primordial giants could explain another mystery, the unexpectedly swift rise of galaxies in the cosmic dawn. Their voracious appetites might have jump-started galactic evolution by funneling vast energy into their surroundings, creating turbulent nurseries for future stars. Yet the biggest question remains unanswered. How did the universe produce such perfect conditions for direct collapse so soon after the Big Bang? Was there a hidden trigger, a phase transition in dark matter, or a fluctuation in the density of the early cosmos we haven't accounted for? Or does this quasar point to something even stranger, like exotic physics in the universe's first moments that allowed black holes to form in ways we've yet to imagine? For now, Euler's J1342+0928 stands as a glaring exception to the rules, a cosmic rebel that forces us to reconsider how black holes, and perhaps the universe itself, were built. With every new observation of these ancient behemoths, we're forced to confront the unsettling truth. The early universe didn't play by the gentle, gradual rules we thought it did. Something wilder, faster, and far more mysterious was at work, and we're only beginning to glimpse its shadow. Galaxies don't just drift lazily through space, they flow, carried by the universe's grand currents. But in the early 2000s, astronomers noticed something unsettling. Hundreds of galaxy clusters weren't moving randomly. They were all streaming in the same direction at blistering speeds, as if pulled by an invisible hand beyond the edge of everything we can see. This eerie cosmic migration, dubbed the dark flow, suggests forces at work that shouldn't exist, forces from outside our observable universe. The evidence comes from the cosmic microwave background, the afterglow of the Big Bang. Tiny temperature fluctuations in this ancient light serve as a reference frame, letting scientists track galaxy clusters' motions relative to the early universe. By studying how these clusters distort the CMB via the kinetic Sunyaev-Zeldovich effect, a subtle shift in microwave photons when they interact with hot gas, researchers found clusters hurtling at nearly 2 million miles per hour toward a single patch of sky near the constellations Centaurus and Vela. The kicker: there's nothing massive enough in that direction to explain the pull, nothing we can see anyway. Skeptics argued it might be instrumental noise or local peculiarities skewing the data. But when the team expanded their study from 700 to over 1,000 clusters using NASA WMAP and ESA's Planck satellites, the signal held. Even more bizarre, the flow extends at least 3 billion light-years far beyond the reach of any known supercluster's gravity. This isn't just a few galaxies drifting together. It's a continental-scale current cutting across the cosmos, defying the primordial uniformity of the Big Bang. So what's tugging on them? One radical theory points to a gravitational anomaly outside our universe, perhaps a neighboring bubble of space-time in the multiverse, whose immense mass leaks gravitational influence through the cosmic foam. Imagine two soap bubbles barely touching. The membrane between them might allow faint forces to seep through. Alternatively, higher dimensional gravity could be at play, where unseen dimensions warp our universe's fabric in ways we can't directly observe. Yet the most unsettling possibility is that we're seeing the fingerprints of a pre-Big Bang structure, a relic from a time before time, whose gravitational echoes still ripple through creation. If true, it would mean our universe isn't the clean slate we thought, but a patchwork sewn with threads from an earlier existence. Until we develop telescopes capable of peering deeper into the CMB's subtlest patterns or unlock the mathematics of higher dimensions, the dark flow remains a ghostly tide, a current without a source, pulling us toward questions we're only beginning to ask. The Big Bang wasn't just an explosion, it was a forge, hammering the universe's first atomic nuclei into existence in a process called nucleosynthesis. Within minutes, protons and neutrons fused into deuterium, helium, and trace amounts of lithium-7, leaving behind a cosmic fingerprint we can still measure today. But there's a glaring mismatch in that fingerprint. When scientists tally up the lithium-7 scattered across ancient stars and interstellar gas clouds, they find only a third of what the math says should be there. This cosmic lithium shortage isn't just a minor accounting error. It's a gaping hole in our understanding of the universe's first moments. Take primordial stars, those elusive giants born from pure hydrogen and helium. Their atmospheres serve as time capsules, preserving the chemical imprint of the early cosmos. Yet even in these relics, lithium levels stubbornly underperform. If the Big Bang's predictions are correct, every corner of space should be awash with this lightweight element. Instead, it's as if something, or someone, swept through the cosmos with a cosmic vacuum, scrubbing away 2/3 of the universe's lithium supply without leaving a receipt. One theory points to stellar destruction. When stars like our Sun die, they swell into red giants, their outer layers churning like a boiling pot. This turbulence could drag lithium down into the stellar core, where temperatures soar high enough to destroy it. The problem, while this explains lithium depletion in later generation stars, the oldest stars, those formed from nearly pristine Big Bang material shouldn't have processed lithium this way. Their atmospheres are too cool, their interiors too placid, yet even here the lithium is missing. Then there's the exotic physics angle. Could unknown particles from the early universe have interacted with lithium, transmuting it into heavier elements or breaking it apart entirely? Actions, hypothetical particles theorized to solve other quantum puzzles, might have played a role, their ghostly interactions subtly altering nucleosynthesis. Others suggest primordial black holes. Tiny, dense remnants of the Big Bang could have gobbled up lithium-rich gas before stars had a chance to form, hiding the evidence in their event horizons. The most radical solution may be we're measuring wrong. Lithium bonds easily with other elements, forming molecules that might evade detection in stellar spectra. Or perhaps supernova, those titanic stellar explosions, hurled lithium into regions of space we haven't yet surveyed. But even with these caveats, the gap remains too wide to dismiss. The lithium problem isn't just about a single element, it's about the reliability of our cosmic origin story. If we're missing something this fundamental, what else might we have wrong about the universe's first chapters? Future telescopes, like the Extremely Large Telescope, could scrutinize older, purer stars for clues, while particle colliders might recreate the conditions of nucleosynthesis with unprecedented precision. Until then, this lightweight element carries heavyweight implications, a quiet reminder that even the universe's simplest recipes might still have secret ingredients. From unexplained cosmic signals to galaxies that defy gravity, from phantom black holes born too soon to vast voids where the universe forgets itself, we've traveled through 25 of the cosmos' most baffling mysteries, each one a humbling reminder of how much we don't know. These aren't just gaps in our knowledge, they're chasms yawning wide enough to swallow every assumption we've ever made about reality. The universe delights in throwing curveballs, whether it's dark matter's invisible grip, the eerie precision of Saturn's hexagon, or the lithium that vanished from creation's ledger. Each enigma whispers the same truth: we're still beginners in a story far grander than we've dared to imagine. But here's the thrilling part: the tools to crack these mysteries are already in our hands. The James Webb Space Telescope peers deeper into the cosmic dawn than ever before, hunting for clues about those impossibly ancient black holes. LISA, the upcoming gravitational wave observatory, will listen for ripples in space-time that might reveal hidden dimensions or the true nature of dark energy. Even now, laboratories buried deep underground chase ghostly particles that could rewrite the rules of physics. The golden age of cosmic detective work isn't ahead of us, it's here. So stay curious. The next breakthrough might come from a lone researcher staring at a data glitch, or a kid watching the stars from their backyard, spotting something everyone else missed. Maybe you'll be the one to connect the dots, to see the pattern hidden in the noise. Until then, let these mysteries unsettle you, excite you, keep you hungry for answers. Drop your favorite cosmic head-scratcher in the comments. Is it the wow signal that still haunts you, the great attractor's invisible pull, or something we didn't cover today? The universe is vast, strange, and far from done surprising us, and that's the most beautiful mystery of all.